Hello, and welcome to our session on introducing the Nginx service mesh. My name's Owen Garrett, Senior Director of Products in the Nginx business unit at F5 Networks, and it's my pleasure today to share with you the plans that we have bringing us up towards the first open beta and general availability of our new Nginx-based service mesh solution. We're living in unprecedented times. And no, I'm not referring to the COVID pandemic or the Black Lives Matter movement or any of the other hugely significant geopolitical changes that we're living under at the moment. There's some good, entirely positive news too. In our industry, the industry of creating and delivering applications that support our organizations, that enable people to connect, to communicate, and to conduct business, we are making immense strides. Huge strides in the form of developer productivity, of innovation, and time to market. To delve into this, we need look no further than GitHub's Octoverse report. They've seen from their own activity that the number of developers on GitHub over the last year has grown significantly, adding 10 million new developers in 2019. The rate of repositories that are being created, particularly by those created by developers for the first time, is huge. Pull requests show the active repositories, the activity that developers and engineers have. 28% more developers opened their first pull request on GitHub last year than the year before. And the rate of closing issues is a great indicator of the quality, the innovation, and the rate of improving software. Behind this is continued adoption of high-level languages, of opinionated application frameworks that help developers focus on the problem at hand without having to worry about the infrastructure. Practices such as agile development, tools such as low-code or serverless that take a lot of the burden away from developers, even platforms and application servers such as Nginx Unit, all contribute to improving developer productivity. And the net result is not measured in lines of code or defects per thousand. The net result is that the speed at which businesses deliver innovation is accelerating. The speed at which businesses can bring new applications and services to market is reducing significantly. A very important change that's helped to drive this has been the widespread practice of uncoupling large, complicated applications, monoliths if you like, into smaller, decoupled, independently developed, independently designed, independently tested, and independently deployed components. Microservices and containers have emerged as building blocks for this new style of building and operating applications. And the two are very often paired together, even though they are independent, autonomous technologies or approaches. And Kubernetes is emerging as the standard for managing microservice containerized applications at scale. How do we know this? Well, from our own surveys. When F5 surveyed their enterprise user base, they saw a shift last year. For the first ever time, more organizations chose containers as their preferred deployment platform over virtual machines or virtual appliances. And in the Nginx survey of our user base, almost half of Nginx commercial users who used Nginx Plus to deliver their applications, were running Kubernetes in production. But of course, the reality is much more complex than a simple shift from a monolith to a microservice. Containers, microservices, Kubernetes are strategically important, but organizations also operate traditional assets that are difficult or maybe even impossible to put through this modernization cycle. The quality of a modern application is that it's hybrid, it's disaggregated. Components may run in a monolithic fashion on an application server or on a virtual machine. New components may be delivered in a microservice fashion on a Kubernetes cluster, but very often additional components and extensions are done using a strangler-like pattern to wrap existing applications. So we see complex, disaggregated, cloud-native patterns running alongside traditional classic monolithic patterns. We see multiple consumption models. We see everything being automatable. And it's this complexity that underlines how modern applications are structured, are architected, and delivered. This complexity inevitably brings a number of operational challenges. We have seen through our own research a significant increase on the number of attacks on applications over the last 2 years, as malicious users and entities attempt to exploit vulnerabilities in the operation or the behavior of applications. And at the same time, with faster development cycles, faster code to production cycles, it becomes increasingly hard to put proper, trusted, secure processes in place to ensure the security of an application. We've seen 100% of the organizations we spoke to identifying that they lack adequate visibility into the performance, the health, and the availability of their applications and services. And that's compounded by the complexity and the number of different components that support those applications. That complexity also brings operational challenges, as different styles of applications, as different language frameworks, as different application servers, as different deployment patterns are running in parallel. And these complexities are particularly acute when we look at Kubernetes-based, container-based microservice applications. You need look no further than the CNCF landscape to see the huge growth in tooling and best practices that attempt to address some of these complexities for applications that are written in a cloud-native fashion, targeting Kubernetes and similar environments. One such technology that is emerging to address some of these operational challenges is the service mesh. A service mesh, at least from Nginx's perspective, attempts to address 3 critical operational challenges for applications that are distributed and are running on environments such as Kubernetes. The first challenge that the service mesh attempts to address is that of securing the application, allowing it to run in a shared container environment where there is a zero trust network, and layering the necessary security on top so that individual components of the application can only talk to components they're authorized to, and all intra-component traffic is secured and encrypted using practices such as mutual TLS. The second challenge centers around observability, measurability, visibility of traffic. No longer can you attach a debugger to an application and trace calls to functions to help understand how the application is behaving and identify failures. When the application is spread across multiple different components that may scale up and down autonomously without warning, then debugging and troubleshooting applications takes an entirely new scale. And the service mesh attempts to layer transparently the ability to instrument and to troubleshoot calls between different services in an application. And finally, in a world where individual components are developed in parallel, deployed and scaled in parallel, the task of operating and managing the traffic within that distributed application becomes immense. These are all capabilities that Kubernetes has core primitives to address. But in a modern, complex, sophisticated environment, those capabilities often do not go far enough, are not fine-grained enough, or granular enough. And so a service mesh allows a developer to specify policies that attach to individual requests or transactions and implement things such as load balancing or circuit breakers to protect vulnerable components of an application, or to switch and route traffic with practices such as blue-green and A/B testing. Behind these capabilities is a critical design goal, and one that made early mesh implementations very difficult to deploy and operate. A design goal of transparent orchestration, automatically injecting the necessary components into the infrastructure and application to provide the level of control that was needed, and interfacing with the APIs or tools that users used to manage those applications in a seamless fashion. And so I'd like now to share with you the work that we have been doing to build a service mesh implementation based on an Nginx-based proxy. As we've done this, the work has been guided by the core principles and qualities that have served Nginx very well for the last 15 or 20 years. The qualities of being lightweight, of providing the highest possible performance in terms of throughput and lowest latency, and the qualities of being simple and perfectly formed for the task at hand. As we go through the architecture of the Nginx service mesh, let's begin with a classic Kubernetes environment. Kubernetes at the infrastructure layer, and a control plane comprised of the Kubernetes service registry and other components, and an API wrapping that registry. When you come to deploy an application on Kubernetes, you'll deploy it as a collection of services, each made up of pods, perhaps a different number of services within each pod, and almost inevitably an ingress controller in front of that application, bridging the network and handling north-south traffic as it comes in to the Kubernetes environment. Our goal, of course, is to gain control of the traffic between these individual services so that we can then layer on the capabilities of security, observability, and traffic control. And that's done through the automatic and silent injection of Nginx-based service mesh proxies into each of the containers that makes up the nominated application. The proxies take control both of traffic coming into the application, ingress traffic, and egress traffic coming out of the application or service. And in addition, we layer on an additional incarnation of the Nginx ingress controller, this time repurposed to handle egress traffic. With these points of control, we now have full control over traffic coming into the environment, being delivered to an individual service or pod, coming out of that service or pod to another service or pod, and ultimately requests that may need to go back out of that environment to external services that must be consumed by the application. All of these capabilities give us the level of control that we need, but they don't address the biggest single challenge that the service mesh must overcome, which is that applications are fluid. They can scale and contract without notice. They can talk to external services that can appear or disappear without notice. And as we wish to apply policies to the traffic that flows through that application, those policies can change the nature of the topology of the application and the traffic meshing requirements of the mesh. And so to meet that, it's necessary to layer an additional control plane into the service mesh to hold the topology of the application, to hold the policies that govern how traffic is managed and routed within that application, to learn from the Kubernetes inventory as to where components are deployed, and then to interface with the individual control proxies, both the Nginx ingress and egress controllers and the Nginx service mesh proxies running within each individual container. When we set about designing the control plane, we took the approach of building what you might regard as a sidecar control plane. It was very important to us that we did not pollute the existing Kubernetes service registry with our own configuration. We wanted to build a control plane that could be scaled and deployed independently of the Kubernetes service registry, and potentially in the future also deployed outside of Kubernetes. We wanted to build something that was lightweight, perfectly formed, and critically importantly, could be uninstalled as easy as it could be installed into the environment, thus reducing the risk and the complexity of deploying the Nginx service mesh, running it through test and evaluation processes, knowing that if it didn't meet requirements, or if a large-scale redeploy was required, then that would be easy to do without disrupting the existing Kubernetes environment. In fact, you can enable Nginx service mesh in a Kubernetes environment, deploy applications which will automatically inject sidecars, deploy policies, perform all of the service mesh capabilities, and should you need, you can then pull the service mesh out of the environment, removing the control plane and leaving the proxies inside individual containers running in very, very simple pass-through mode, making the task of deploying and removing the service mesh as simple as it could possibly be. In order to provide mutual TLS security for the communications between the individual components in the application, we've used the Spire framework with Spiffy to distribute certificates and implement mutual TLS for traffic between the ingress and egress controllers and the individual service mesh proxies. We provide a simple default install of Grafana and of Open Tracing within the service mesh deployment. Of course, it can very easily be pulled out and you can replace that or point it towards your existing infrastructure tools. This provides the observability and the debugging necessary to control how the application, to observe how the application is operating. Looking at the timeline for the Nginx service mesh, we will announce an open beta of the mesh with a target date of the end of September 2020. And then this will take us through a period of in-production testing and hardening and feedback towards a target general availability date of the end of 2020 or early 2021. Within that open beta and GA release, you'll find a fully autonomous control plane with automatic integration with Kubernetes, auto-injection of the data plane components within individual containers. You'll find security management capabilities. So building on the Spiffy and Spire projects, certificates can be issued, revoked, and expired. Mutual TLS will be implemented between every individual component of the application, and firewalling will allow you to run in a zero trust environment where other services managed by other parties are running on the same Kubernetes environment. Integration between both the ingress and egress controllers and the service mesh through a single consistent API, so integrated north-south and east-west traffic management, will deliver operational efficiencies. With a single API and a single observability interface, you will be able to configure, secure, and tune how traffic comes into the Kubernetes environment, how it's distributed across the forward-facing endpoints of the composite application, how it's then spread across the application in an east-west fashion, and control for any calls, API calls, or HTTP requests that need to be routed out of the Kubernetes environment to external services. The SMI spec provided the core design and inspiration for the way that we distribute and control how traffic is split and routed, and the way that we observe and provide metrics for traffic. So with an SMI spec compliant implementation, the service mesh will help you in an operational environment to deploy new instances of a service and move traffic across in a blue-green fashion, to prove new instances with A/B testing, to implement canary testing for an initial instance, circuit breaker patterns to wrap an instance with a default response and protect that instance from being overloaded in the event of a failure, and to implement targeted rate limiting, again, protecting or controlling how much resource individual services or requests can consume. Metrics and observability will interface with standard Kubernetes and CNCF tooling, such as Prometheus and Open Tracing, to give you traces, metrics, and observability instrumentation to identify the performance, the bottlenecks, and to troubleshoot individual services. We have a goal of broad platform support, We're actively testing the service mesh implementation on both hosted Kubernetes platforms, on-premise and third-party platforms. And with everything coming through the Kubernetes API, that helps you have a standard management interface for not just the mesh configuration, but everything else which you're already doing against Kubernetes. As we look towards the futures, as we go through the hardening period of 0.6, the general availability and the availability of a supported service mesh with a target of the end of 2020 or start of 2021, then we look towards additional capabilities to extend the mesh beyond Kubernetes to endpoints of the application that are not just accessible through the egress proxy, but rather can be reached directly through the mesh to an endpoint outside of Kubernetes. Supporting additional protocols, UDP-based protocols, for example, so that the mesh can handle traffic such as DNS or media delivery. Configuration that also addresses the challenge of taking an API specification, so a Swagger or an OAS specification, and converting that into rules that should be pushed into the service mesh. And taking advantage of the additional capabilities that you find in the Nginx proxy. The proxy, the data plane, is far from being a simple packet pusher. With Nginx, we have capabilities for request-based authentication, security policies, advanced WAF, rate limiting, and all of those could be tactically targeted into a mesh-based deployment. For example, by deploying WAF rules at the edge for ingress traffic, so that any traffic coming into the mesh environment has been scrubbed and secured. And further in the future, there are immense opportunities to take the mesh technology and to make that manageable and visible through the Nginx control plane. A mesh is by far the only thing that you need to deploy an application. As you think about the delivery pipeline for that application, you've got to think about application delivery, so ADC, load balancing, API management, API policies, and security policies, in addition to the capabilities delivered by the mesh. And the goal that we hold high is that Nginx controller will be able to give you a single API-driven configuration layer that can manage and monitor and visualize and trace all of the critical services that are necessary to deliver a modern enterprise application. And finally, there's huge promise as we look at the capabilities within Nginx Unit. An open source application server with its own built-in proxy and the ability to run multiple instances of an application and to scale them running different applications concurrently on the same footprint. Where we could configure and manage Unit through the mesh, then that introduces a lot of exciting new possibilities to change the way that applications can be packaged and deployed and scaled. And this is an active area of research within the Nginx product group. So I'd like to thank you for your time today. I've shared with you a taster of what we will be releasing later this year in the form of an open beta of the Nginx service mesh, working towards a fully supported production-grade mesh at the end of this year or the start of next year. And with an ambitious future roadmap and a clear vision on how we can take that mesh technology and fold it into additional Nginx estate and Nginx control plane tools to produce a rich, automatic, adaptive, scalable interface for deploying, managing, and delivering applications. So please, follow us on nginx.com, watch out for the future notifications on availability of the mesh, and I look forward to catching up with you, whether it be through GitHub issues or webinars or briefings that we can do to share with you what's coming in the future with Nginx Mesh.